record this in the computer. Okay, now we're back. Okay, so I want to slowly, although we are familiar with the concept, but we are familiarizing ourselves and also how we interact with each other. So I want to slowly introduce to you this first topic. Okay, so again, just to recap, we have data points. Okay, we have input data of X and a measured value of a target value of T. And what we want to do is we want to estimate that data points of X value, given X value and weights. Okay, and now you have an estimated function of your W that is a function of those input X and W. And remember, W is a vector. Okay, so we should W is a vector. Okay, so this is your target. This is your target, and this is your estimated value. Okay, now the question is, what kind of polynomial is the best way of estimating the given data? Okay, so now we constrain ourselves to say, hey, wait, we want to say, so our polynomial is y of, okay, maybe here, y of X and W. So I will write it as is equal to the summation of J is equal to 0. And write it as a summation Wj, okay, W sub J and X to the J. Okay, up to M. Okay, so we don't know what's the value of M and we don't know what's the value of W. Okay, so now there are two things that we need to know in order to find the best estimate. First, we need to know what is that M value. Okay, and the next one, once we determine what is the N value, we also determine what is the value of W. Or we can go through each of them. For example, that's what we are doing here. Let's go for M is equal to 0. Now M is equal to 0 are all these lines, and then these lines, these lines. What kind of M, what kind of W0 is the best estimate? Then you come out with many flat lines. Okay. Now let's estimate M is equal to 1. So what kind of lines that will give us those good estimates? Yeah, you have all these lines here like that. Okay. Okay, now you have our estimates. Now let's try M is equal to 3. So what kind of cubic functions that will estimate our data points like that? Okay. Now let's try M is equal to 9. So M is equal to 9. If, as you can see, M is equal to 9, the function goes to every data point. Okay. This is what we call overfitting. Okay. The function really have a good fit on the data points, but it is not a good fit of the real function. The real function is your sinusoidal function. Now, this is too much away from the sinusoidal function. So the question is the bigger the M value always the best estimate? The answer is no. It is not all the time. Okay. Well, how do we know which one is the best estimate? Well, what you can do is go through each from M is equal to 0 and investigate M is equal to 1 and see which one best estimates, and go to M is equal to 2, M is equal to 3. Yeah. So for example, if we want to do M is equal to 2, for example, here, so if we say M is equal to 2, then we'll fit like this. Yeah, some quadratic function like that. Which one is the best quadratic function? Like that. Or should it be like this? Or like that? Or like that? Okay? Okay. So now we know that how to play around with the degrees, or what kind of polynomial we want, and what kind of specifically what are the values of the weights to give us these graphs of the function. And then now, how do we measure? The question is, how do we measure? What exactly is the best estimate? How do we know that this one is the best estimate compared to this and this and this? How do we measure that? We need, although we can visually see it, but we need to have some numerical measure. Okay, we cannot just, like beauty, you see, oh, they say beauty is in the eyes of the beholder. Well, maybe because different persons have different measures, yeah, of a beautiful person. But can you convert it into some numerical value? Okay. Well, they say art cannot be measured by some numbers. Okay. But probably you can. Yeah. But how? Well, maybe you assign certain things of, what are your parameters for beauty. Anyway, so this just even love can be measured by a number, for example, or feelings can be measured. Yeah. Nowadays, everything can be measured. Given a good like a sensor, maybe you can measure even your thoughts. Yeah. Well, and thoughts now can be measured. Okay, with some brain signals, it can be measured. But how accurate they are, that's another area. But anyway, so now we say that how do we measure to say that indeed we can say that yes, this is the best estimate. Okay. Well, let's go to error function. Okay. There is a value of the error, okay, for every estimate that we created. For example, here, this red line and this is the estimated line that we have. Okay. So now this is a value. I mean, it is the function is not big here. I want to say that is the function of y is equal to x and w. Okay, that's the estimated value. Now, these are data points. So the distance between this point and the actual point on the estimated value is the error. This is error. Okay, and also this is error because that's how it is far. So instead of, we say for x sub n, the estimated value is here, but the actual value is here. So the farther they are in the estimated value to the actual value is the error. So now we can say that. Let's go back to the previous slide. Now we can say, so now it is based on error there. Then, so, well, what we can do is that we can measure the error. So here, there's one line here, one line here, one line here, one line here. There. Okay. Then we can add them. Okay, this one line, small line, and then another bigger line. Okay. Then another big line, another one, then a third one. Then this one is very small. Next one is quite big. That next big, next smaller, a little bit small, then big, a little bit big, then a little bit small. So this value here is your total error for this graph. Yeah. So the same thing here. So let's just measure this one. This one, small error, very small, small error, small error. From the estimated value, okay? With respect to this is almost 0. So now if we measure that, let's measure from here, small, another small one, almost 0, another small one, there, another small one, small, almost 0, and 0. There. That's the estimated value for this. Okay, it's very small. Compared to here, same thing. So let's measure here, small, small, and long, a little bit long, small, almost zero, long, short, short, and long. Okay, there. And what about this one? Okay, well, here, look, the error is zero on the data points. It's very good, isn't it? But it's not the best fit. But according to the error measure, the error is zero. So how do we say that in fact this is a good estimate or not? Well, from the training data, the zero, I mean, this one is best fitting. It is the best among everyone. But we can see from the graph it is not. But from our error measure, it is the best. How do we test it that it is not the best? Anyone? Okay, remember, if we go back to our graphs of data, remember this block diagram, data, and then you create the model, and then you predict. Estimate. Inside here is estimate. Okay, here is your training. And then you predict. There. Okay, so because here we are still training. Okay, we get the data, we are training here. We use the error term. Okay, we check about the errors. That's fine. We check the error and we check the error. This is the training part. Now, there's another part of predicting. Okay, we need to predict how much, okay, using new data, not just the training data, how good is the estimation. Okay, so for sure here, if you take a new data, if I take a new data from a sample here, for example, then the error will be very big. Okay, so this is the part of the estimate. I mean, this the predicting of the value. So now you get a new data that is not part of the training data. That data, for example, somewhere in between there, that was not seen during training, it will be very big. Okay, so, but anyway, let's concentrate on, we are not there yet, but I'm just giving you an overview, because here it's almost, you know, I mean, the error estimate is zero. And then how come we say that this is not a good estimate? Okay, the reason is that for an unseen data, for new data, if you checked it against the computed data or computed the model that you created based on training, it will perform very, very badly. The error is very, very big. Okay, so let's not dwell on that one. So let's concentrate on the error term. So first, so your error term is, of course, now this is the value of the output, which is this on the term on the graph itself, minus the target value, which is the value of the data. Okay, remember, this is for the same x. Okay, for the same x, you have a target value or the computed value or the measured value against this one is your estimated value. Okay, the measured value, which is this one, minus the estimated value, okay, Could it be t? Could it be like this minus y of xiw? Could we do that? Squared? Yes, we can. Okay. Okay, we square it. Why do we square it? To get rid of the sign function. I mean, to get rid of the sign. Because if you don't square it, then if you add values without squaring, then the positive value will be subtracted by the negative value. And it will sound like there's no error. Okay, so we square it. So we square it to get the absolute value of this, and the absolute value of this, and the absolute value of this, and add them together instead of them canceling out each other. Okay, so now this is your polynomial function. Now for every point, now you see I is equal to 1 to n. Okay, take note that the m is for the order of the function, and the n is the number of data points. Okay, where is Chipang and where is Jason?
I'm available, sir.
I am available too.
Why are your cameras not on? What are you doing? Okay, I want to see you.
I didn't notice that it's off.
Okay, it's Camela, always the exempted one, yeah?
Sorry?
You're always the exempted one, Camela. Okay, next time you can go to my office if you need that, if you don't have a camera. Okay, there's always a computer.
Okay. Okay, no problem.
Yeah. Okay, Chipang, where are you? I need to see you. Okay, anyway.
I'm available.
I'm available, but your camera is not available. I want to see. Okay, so now, so do you understand this part here? Why we are squaring the error term? Do you understand? Why do you square the error term? Okay, for example, okay, let's have an exercise. So this one, let's say, for example, this is 0 value, and this is a value of 1. Okay, and somehow this one is a value of, maybe this is 0.5, maybe this is 0.9. Oh, let's make it here so that you'll have a negative sign. Let's make it so that you'll have a negative sign. Let's not make, so somewhere here is this one. Let's make this one to be 0. Okay, and this one is 1, and the other one is negative 1. There, that's easier. Okay, so this is a 0.9. Okay, so if we add, we'll just say you have, okay, you have 3 points, 3 data points. Let's just say this is 0.1, and this is 0.2. Although they're not equally spaced, but let's just assume that's 0.3. Okay, so now for the error term, so this error is what? The first error is, you sum all the errors. So the error here of the estimated value minus the target value. So here, let's say, for example, that's, if that is 0, this is 0.4. Okay, and this is maybe 0.2. Okay, negative. Okay, so the error here, the first error term will be the estimated value, which is minus 0.4. Okay, minus 0.9. Okay, there. okay, plus, okay, now this is a 0 minus -1, okay, plus this is a 0.2 minus 1 there. Okay, without squaring them. So what is this now? So minus, this is minus 1.3. There's negative sign plus this is 1. Yeah, plus this is minus 0.8 there. Okay, so now you have 1 minus 0.3, so this is minus 0.3, so now this is minus 1.1. Okay, if you square it, even if you square it and take the square root, so for example, if we square this one, or let's just say absolute value so that it's easier. Take the absolute value, take the absolute value, take the absolute value. Okay, so now you have 1.3 plus 1 plus 0.8. Now that's the real value of the error. So you have 2.3 plus 0.8. So what is that? 3.1. There. A big difference. And this is negative 1.1. Okay, so that's why we take the absolute value. We square the error. Okay, now, so now this is the value. And so we say that, I mean, this is the equation. We say this is the function minus the target. We square them. And then we add all of them together. So that's just the total error. Okay, so the 1/2 is just included just for convenience, so that when we take the derivative of this, the 2 will go away. Okay, now we need to solve for the W that is the optimal. In order to, we need to know to take the derivative of this to get the optimal value of the W. So we take the derivative of the error with respect to W. Okay?
Yes.
Okay, so if we take the derivative of that, there. So what is the principle of the idea of taking the derivatives, and then it will give us the optimal value? What is the principle behind it? Why do you think that when we take the derivative, somehow it will give us the optimal value? Okay, this is all about taking the derivative of the error, this slide here. But what is the principle behind it? Why do you think that when you take the derivative, somehow it will lead us to some optimal value? Why? More easy.
Because of, okay.
Anyone who's why is it first?
What was the question, sir?
If you were in the Miss Universe, you already lost the competition. Are you a contestant in the Miss Universe, Mr. Moise? Okay, luckily we're not in the Miss Universe.
What?
I'll give you another chance. Yeah. So, what is the principle behind taking the derivative of a function to say somehow it will give us, it will lead us to the optimal value? Do you remember anything from your previous mathematics courses to say you take the derivative, and somehow it will lead you to the peak or the bottom of the function?
Sir, I don't have an idea.
Okay, can you have a guess?
Sir,
what is associated with?
I think it's because
Yes. Huh?
it's because it's believed that at the top or at the bottom of a function, the derivative is always 0. So if you plot it, it's going to make at the top, it's going to be turning, and the derivative is going to be 0.
Yes, that's correct. Especially for continuous functions. Okay. So now, very good, Mbate. When you take the derivative of certain functions, when you are at the top, normally, okay, so when you are at the top of that function of a hill, for example, and then the derivative of this function is the slope of the line tangent to it, right? Why is it? Do you remember this? That the derivative is the tangent line, the line that is tangent to the function. Remember this?
Yes.
Okay. And then now you say when you reach the top, you see the slope of this one, of the line tangent to this one, is quite high. And then slowly it goes smaller and smaller until when you reach the top, it becomes flat. Okay. So that means here the derivative will be somehow approximately equal to 0. Okay. So now, if you use the derivative, when the derivative somehow becomes 0, it is a sign of something. Okay. It gives us a flag. Hey, your derivative is 0 now. You must know that your derivative is 0. Okay. So maybe there's something there. Can you look? Okay. That's what it is. That's why we are dealing with derivatives, because we want to know once the derivative becomes 0. Hey, can you see where we are now? Like this, yeah? Because it's like here we are groping. It's dark. We don't know what's going on around us. So we want to be guided by the derivatives. Somehow we keep on, keep on moving around. What's the derivative here? Oh, what's the derivative here? Like that. What's the derivative here? It's high. Oh, we go here like that. Yeah. Now the derivative is 0. Come on. Where are we? Like this. Get your flashlight. Where are we? Like this. Yeah. So now you put your phone. Yeah. Nobody has a flashlight now. Yeah. Everybody will just turn on the phone. Say, where are we? The peak? Are we at the bottom? Like that. We're at the bottom. We're not at the like that. Yeah? Because maybe your battery, you imagine that your battery is already running out. We don't want to use your battery, your phone all the time, because once your derivative is already something, that's the only time that you wake up. Yeah. Otherwise, now your derivative is already something, and then your battery is all flat because you've been using it all along. Yeah. So you save the battery. You only do it when when your derivative gives you some signal. Okay. So now if you go down, the same thing when you are at the valley. So the same thing. Maybe the slope is negative, but somehow when you reach the bottom, it's somehow close to 0. Okay. So exactly the same principle here. We are looking at the derivative here. This is the derivative. When the derivative becomes approximately 0, you are there at the optimum. Okay. So now it's easy to remember now. It's easy to see the reason why we are dealing with derivatives. So now we take the derivative of this error function. It's the error that we are taking the derivative. Okay? Because when the derivative of the error becomes 0, what does it mean? Some of the error peaks. Okay, the error peaks. Okay, somehow we are at the maximum error or the minimum error. Okay, we are at the peak of the error function. Okay, we want to know the peak of the error function because somehow it will tell us, hey, are we here? Are we at the optimal value? Okay, so now the error function has the same thing. Okay, so once the error is here, the error is still very big. The error, the function, the derivative is still very high. Okay, so somehow the error becomes biggest, or if that is the biggest, you can look at it the other way. The error becomes smallest. Okay, how do we say that this is biggest and smallest, sir? Well, just multiply it with -1. Finish. Okay. But anyway, okay, if you want to say, oh, you're at the peak, multiply it -1, you're at the bottom. Okay, but we want to take the derivative of the error because once the derivative of that error becomes 0, we are at the peak or we are at the bottom. Okay, we are somewhere where we want to be. Okay, and that is the optimal solution of the W, because we are looking at the W, the value of the W that we are looking at. If the W somehow, peaks somewhere, then if the error somehow peaks at a particular W, that W must be the best W that we are looking at. So where is the W, sir? Okay, let's clear it first. I'm now carried away with my explanation because somehow I can see that you are understanding. This is our equation for computing W. Okay. So remember, we have input X to compute the estimate, and you have the value of that vector. That means there are many values of W's there in order to come out with your estimate. Okay, X and W. Okay, so we need to solve for the value of W. Okay, first of all, we need to assign the value of M. Okay, for us, we decide what value of M is, maybe 1, 2, or 3. So this is assigned. Then afterwards, we compute for the W. That will give us this error term. Once it peaks, once they become 0, approximately equal to 0, then we are at the best W that we are looking at. Then we label that as W star. Okay, how does it is done, sir? Where? Well, this is, so we are already convinced about the derivative. Yeah, then there's just some learning rate that you multiply. So you multiply this one, compute the error term. Okay, this is the derivative of the error term. The derivative of the error term is this function here. I will discuss it next meeting. Now this is the current W, U minus the present value of W minus this correction factor. Now you get a new W. Okay, now with this new W, you compute this one again. Okay, with this new W, you compute and then compute a new W. This new W becomes this, you compute this W, I mean this current W minus this correction factor, whatever the value of W is. Now you get a new W. Now this new W becomes the current W. Now you compute what is the error term, the derivative of the error term with this current W, and then you correct again, you get a new W, and so on. You continue. It is a recurrent process until your error term becomes approximately 0. So when your error term becomes approximately 0, you are at your W, optimal W. Yes, Mr. Mopati?
Do we start with a guess? The first vector we start with, is it a guess?
Yes.
Okay.
Don't guess with 0. Most of the time, you cannot get out of it. Okay, guess with some non-zero number. Well, it is about guessing. I mean, this is a time this is the nice thing about these courses nowadays, because it's not nowadays people are really computing. We are computing, like numerically computing. We are more interested of the closest solution. We are not really interested of the exact solution. Okay, so the better your guess, if you guess somewhere, okay, it's not, now people are, it tends to, oh, it's 1 o'clock already. I don't want to tell you a story now. The story will be next meeting. But yes, it is about estimates. So you just guess the initial value, and then you search, and then you compute and find the optimal value. Sometimes you get an optimal value, sometimes you don't get. So you guess again another value, and then you compute like that. So you guess again another value. So yeah. So it's just about guessing, and then which guess will be the best will find you somewhere, will lead you some optimal values of that. Jason cannot believe it. So in this class, we're just guessing. Yeah. Yes, we are guessing here. Yeah, we are guessing. It's true. We are guessing, but with that guess, with our computation, it will lead us somewhere. Okay. And now we need to analyze that, where we are. Okay. And sometimes you need to readjust, guess again if you're somehow not there yet. Okay. And that's the nice thing about these days now. We are always, there's no right or wrong answer. It's just there's better and best solution. Okay. Most of the time you cannot find the best one, but the most probably a better solution of all the rest. Okay. Okay. Now I'm just giving you the overview of this initial topic. Next meeting, we will continue with, we will discuss with some, this is very short, with some computational examples, and then so that you can understand exactly. Once we finish this topic, you will be, have an overview of what exactly is the basics of the modeling, of creating modeling in machine learning and testing those models. And then we can go now, because I like this linear regression or polynomial regression, because it's a simpler topic, and then you can somehow be led to have a framework of what's going on. And then as you continue to much complicated solutions, then it's always that framework is there. Okay, you already have a good foundation. We can go to much more complicated computations. Okay. So if you find this JSON to be complicated, we have much more complicated computations later on, which I'm sure you will enjoy. Okay. Okay. So that's it. And then attendance again, smile. Smile. Okay.